Hello everybody. We're going to skip chapters 10 and 11 and go right to chapter 12. 10 and 11 have to do with magnetics, transformers and the like, which you may find important to your career, but most people don't. Most of the time we deal with electronics. We deal with equipment like motors and the like that are inductive in nature. So the need for a deep understanding of magnetics is not as important as what we're moving on to. Okay. So what we're going to be talking about here is frequency performance and filter functions and the like. And first of all, let's look at the basic components, what their frequency response is, the impedance, that is. So resistors, the voltage and current are in phase, so you have zero phase angle. And the magnitude of the impedance versus resistance is a flat line. It's always the same. In reality, by the way, there's what's called parasitic capacitance. So what you think is a resistor doesn't extend to infinity and beyond. There is a point where it can't transmit a certain amount of frequency, either because of its inductance or because of capacitance. Phase angle, zero, always zero. Okay, inductor. It has an impedance which is linear with respect to frequency and always a 90-degree phase angle. The current always leads the voltage. Capacitance. Impedance is negative 90, just the opposite. Magnitude is 1 over frequency. That's this curve here. And phase angle negative 90. Okay, now we start making circuits of this nature, for example. And we can write the impedance like so and get j omega c as a common denominator and get rid of the imaginary numbers in the denominator. So we get the form of this equation right here. So the magnitude of the equivalent impedance is going to be the square root of the sum of these two squares divided by omega c. And there's your amplitude. Frequency on the x-axis, magnitude on the y. This lowest point is where omega c equals 1 over root LC. And you can see when that happens, this term goes to 0. It minimizes ZEQ. It's when ZEQ is the minimum. The angle is just going to be the arctangent of the ratio of the imaginary to the real part, and is given like this. At first, it's purely capacitive. The inductor acts like a resistance is 0. Then as you go up in frequency, the capacitor impedance drops and the inductor impedance starts taking over. So it switches over to inductance. Now, this is kind of important right here. It's a notation thing. It's important, but it's also has to do with notation. That we use the parameter S to mean the imaginary constant times the angular frequency. So from now on, just remember, that's what S is. So now we have a simplified notation for the impedances. And here's something else. We can rearrange the impedance to always equal the ratio of two polynomials in S. So, for example, if you have this, here's the impedances of the components right there. And we can write V out as a voltage divider equation, the resistance here, divided by the total impedance. So V out equals V source times the voltage divider equation. Let's see, rearranging gets rid of the S, multiply top and bottom by SC. It gets rid of fractions, rationalizes. A little bit of algebra there. What it really means, and I don't know why they put approximately equal to j omega. It's supposed to be exactly equal to j omega, right? They're using the approximate. It can be exact. It is exact. And so putting in all the component values, we get this. J omega in the top, RC, R is 15 ohms, C is 2.53 millifarads, all the scientific notation stuff. Here's C, here's L, and so forth. Let's see, 15 ohms times C, and then the J omegas are floating around. Now, we can use MATLAB. So you can use what's called the freak function in MATLAB. And there's the freak function. It's in the signals, excuse me. It'll cost you money from MathWorks. New Octave, remember, is the open source MATLAB lookalike, and you can download the signals package for free. And I've written some handwritten code. If you really want to stick with MATLAB, you can take the files that I've done and go ahead and in 2 more slides. There's one other slide, and then my code is the next. So you can copy and paste that into your copy of MATLAB to be able to use my personal handwritten code. Okay. V out is this, and they forgot to write times the source voltage. They got to do that. So this is from the previous slide, just the formula from the previous slide. This is the coefficient of there we go, A1 in this polynomial. And there's only one. A0 equals 0. Make a note of that. For the computer, that's going to be important. And then we have B2, which would be one of these dots right here. B1 and B0 right there. So we define the numerator polynomial. We just write down the coefficients. Write down the coefficients here. We need the 0 here because A0 equals 0. You can't just ignore it. It's got to be there. Denominator, similarly. So this would be B2, this would be B1, this would be B0. And then run this function. It's in the signals package of New Octave or MathWorks, or you could use my code. I have a little, it's different. This uses, by the way, angular frequency, radians per second. I wrote my code to take hertz. Most people think in hertz. Okay, missing coefficients must be entered as 0. And this point here is that in MATLAB you can use a space instead of a comma. But you can't have a space here, any other places. No other space is allowed. Just where you want to separate two distinct numbers. And here's the plot. Later on, we're going to talk about decibels. Decibel is power, is a ratio of power on a log scale. And so power goes as V squared or I squared. So for every time you change the frequency by a factor of 10, you're changing the gain by a factor of 10 in this plot. The voltage gain. But the power gain is 20. So they call it 20 decibels per decade. Okay. And there is a slope. Kind of a straight line right up here. And then on the downside, similar. In fact, it's the same slope. One going up, one going down. And then the phase angle, where you switch over. And right here is the resonant frequency. Right where the phase angle crosses 0. Right where this is maximized. Okay. There's the circuit on the right. This is my code. I'm going to go through it. I'm not going to spend time on it. Just you can copy it into your copy of MATLAB and use it. This is some testing just to make everything work out right. This is the example that is used on the MathWorks site just to double check that my stuff works the same, and it does. Now, let's go ahead and stop here. I will pick up this example next.